Hi, Chemistry 11. So, it's been a while since you heard from me. Things have been pretty crazy with other aspects of the job, but I'm back. And this week we're going to get through a worksheet and a lab. So, without further ado, we're looking at percent composition, empirical formulae, empirical mass for the worksheet and the lesson today. I have a worksheet I'll be putting on Teams. I'm going to outline some of the problems from it, which I think is maybe the best way to help you out. So the reading for today is pages 90 through 95 of the textbook. Also, I do really suggest that you be watching the DeWitt videos on this same topic. Percentage composition, as you'll see in the notes, they are listed as the percentage by mass of a species in a chemical formula. So what does that mean? Well, first of all, the species is usually, and for the purposes of today's lesson, going to be an individual chemical element. So you might examine, for example, H2O, water. In water, there are 2 hydrogen atoms, 1 oxygen atom. Each hydrogen atom has a certain mass. Hydrogen has a molar mass of 1. Oxygen has a molar mass of 16. But there's 2 hydrogen atoms in each of those water molecules. You get the percentage by adding up all the molar masses of the atoms for that element and dividing it by the molar mass of the compound. That will give you the percent composition for each of the elements in the compound. This works whether you're given an empirical formula or a molecular formula. But what does that mean? Well, an empirical formula is just the simplest whole number ratio of the different elements in a chemical formula. So we can examine or imagine a situation where we have, say, a substance that has an empirical formula maybe of C2H4, welder's gas. A molecular formula of C2H4, welder's gas. That molecule would have 2 carbon atoms and 4 hydrogen atoms. Now, that would be the molecular formula. 2 carbons, 4 hydrogen atoms, C2H4. The empirical formula is just, again, the simplest whole number ratio. So the empirical formula for that substance would be CH2. A 2 to 4 ratio is the same as a 1 to 2 ratio. Now, with the you can use the percentage composition to figure out what the empirical formula is by using the molar mass for each element. You're going to need for this your periodic table. The one I used as a reference table went to 1 decimal place. This issue came up with an answer key as a question that some people had. So I'm using this one here on page 172 of your textbook, of the Science 10 textbook. Some of you made a copy of that. If you didn't, no sweat. You go online to Dynamic Periodic Table. It's an awesome online periodic table, and just round your values to 1 decimal place. The answers I show here will be rounded to 1 decimal place, and that is actually the most convenient and realistic for what you're looking at. We're going to look today at calculating percentage composition, and also at empirical formulae, and using some extra information to find molecular formulae. Remember, the molecular formula is going to be the actual chemical formula that communicates the number of atoms in a molecule of each compound for each element. The molecular formula for water is H2O. Each molecule of it has 2 hydrogens and 1 oxygen. Now, let's get started. What I'm going to do is I've answered a number of the questions. I'm going to put the camera close up to those questions and show you my answers, and then we can go back to that later as I discuss those answers. There. That is today's work as I've written on the board like I would do on a normal day. Here. This is the answer to question 1A. You might want to pause the video here. This is the answer to question 1C. You might want to pause the video here. My answers are written in red. I also decided I would answer question 2C. Here is the answer to question 2C. Then I answer question 3 on that same worksheet. There is the answer to that. Question 3 naturally leads in to question 4. Again, notice the answer in red. Question 4, the answer is outlined right here. All right, let's actually keep doing this. I'm going to switch on my light. I also answer questions 9 and 14. There. This is my answer for question 9. That light's not working out so well. Here is my answer for question 9, right here. A problem-solving question using unit conversions. Right here, this might have been hidden by the reflection in the light, but there you can see it now. The answer to question 14, also a more complicated problem-solving question, which we're going to get to. Here it is. Here's the top part of the answer, like right there. Here is the bottom part of the answer right there. Again, you may wish to pause the video to write down the answers if you have problems with them yourself. For percentage composition problems, the simplest thing to do is to assume that you have 1 mole of a substance. So right now I'm on question 1A of the worksheet. We are given an empirical formula of CH. CH is not a substance. It's not a molecule. You can't just have a stable molecule that's a carbon bonded to 1 hydrogen atom. It doesn't exist. But as an empirical formula, yes, that can exist. A chemical that has a 1-to-1 ratio of carbon to hydrogen. That's a real thing. It's called ethine. Now, we assume we have 1 mole. For those chemical amounts, which we need to calculate, we find the total mass of carbon. There is 1 atom of carbon. Go to the periodic table. It will tell you carbon has a molar mass of 12.0. It would be good to memorize that molar mass because one you will be using very commonly. Hydrogen has a molar mass of 1.0. This is easy to add up. The sum of them is 12 plus 1 is 13. So I shouldn't say molar mass, empirical mass. There's a correction right there. I'm correcting that. The empirical mass is 13, 12 plus 1. The percent of carbon that there is in the substance is 12 divided by 13 times 100%. The answer written in red is 92%. This means that 92% of the mass of that molecule is carbon. After all, carbon is a much bigger atom. The percent of hydrogen, the only other element, is 1 over 13 times 100%, which gives you 8%. Question 1C is this. We have a compound, C2H60. The empirical formula is C2H60. The ratio of by number of atoms of carbon to hydrogen to oxygen is 2 to 6 to 1. This doesn't tell you the molecule shape, doesn't tell you anything about the molecule itself other than the ratio of the elements in it by number of atoms. The total mass of carbon, again assuming we have 1 mole, is 2 times 12, 24 grams. That of hydrogen, 6 times 1, 6 grams. That of oxygen is 16 grams. So this is 46 grams per mole, but I don't want you to mistake this for a molar mass. If the chemical formula has more atoms in it than this, if the chemical formula and the empirical formula are not the same thing, this molar mass won't be correct, but we can still use it for calculating percent composition. 24 divided by that 46 will be multiplied by 100%, gives you 52% is the percentage of carbon. Percent of hydrogen, 6 over 46 times 100%, 13%. And of oxygen, we have 35%. So C2H60 might give you the actual number of carbon, hydrogen, and oxygen atoms in the molecule, but not necessarily. This is an empirical formula that's been calculated, but it's good enough for calculating the percentage composition. Now, in question 2, I want to be clear that here we're not dealing with empirical formulae, but that doesn't matter. We're dealing with molecular or chemical formulae, the actual number of different atoms, of different elements or chemical species that is found in one formula unit or molecule of the substance. Here we really should say formula unit because it's ammonium phosphate, which is an ionic compound. NH4, 3, PO4. The NH4 is the ammonium ion. Each ammonium ion is 1 nitrogen and 4 hydrogens. They only have a +1 charge each. Phosphate, PO4, has a 3-. In the formula, we have to balance 3 ammonium ions with 1 phosphate ion. Hence this very complicated, or at least relatively complicated formula. NH4, in brackets, 3 PO4. Here's where you would want to make certain not to make any mistakes about what's going on with that polyatomic ion. Again, we're working now with an actual molecular formula, which means that here we really are finding a number of grams per mole of ammonium phosphate. That's the real thing because we're not looking at empirical mass anymore. This is molar mass. How do we get there? There are 3 nitrogens. How do I know? And inside here, there's one of them times 3 is 3 nitrogens. There's 12 hydrogens. How do we get there? Each ammonium ion has 4 hydrogen atoms. Multiplied by that subscript 3 again. 4 times 3 is 12. Each of those hydrogen atoms has a molar mass of 1.0 grams. So we go 12 times 1.0 grams gives us 12 grams. That is the hydrogen's contribution to that molar mass. Phosphorus we get directly from the periodic table. There's only 1 phosphorus. I want to be clear about that. That 4 right there does not apply to the phosphorus, only to the oxygen. So oxygen has a total mass in this formula of 4 times 16 grams. That would be another good figure to remember, 16.0 grams, the molar mass of oxygen. Hydrogen 1.0, carbon 12.0, oxygen 16.0. Good ones to memorize. They all add up, 42, 12, 31, and 64, to 149 grams per mole. The real molar mass for this compound ammonium phosphate. Again, you're seeing we're calculating this the same way. The percent of nitrogen, 42 over 149 times 100%. Of hydrogen, 12 over 149 times 100%. The percentages we get, 28%, 8%, 21%, and 43%. So that's questions from the first page of that handout. The other questions are very similar to that, so I hope that you can use those directions to get the results for those questions. Again, this is going back to that same problem as before. I'll walk you through it. So, this is not what I wanted to do next. I want to do this right here. Questions 3 and 4. What you're doing here is you're going backwards. You're being asked to calculate the empirical formula. And then the second step problem is to calculate the molecular formula based on some extra information. The reading for this is on pages 91 and 90, really 91, 90, up to 93, 94 of your textbook. For these kinds of problems, you assume that you have 100 grams, which is, it's a lot easier, really. You could assume you had any amount, but 100 grams is super easy because, after all, you were given percents. If your carbon is 65% by mass, 65.5, then you have 65.5 grams in 100 grams. Hydrogen 5.5 grams and oxygen 29.0 grams. How do we use that? Well, one of the formulas you've learned is this: that the number of moles, the chemical amount, is mass divided by molar mass. We use the molar masses for those elements from the periodic table. So for carbon in our 100 gram sample, 65.5 grams divided by 12 grams per mole is 5.46 moles of carbon. For hydrogen, we get 5.5 moles. Notice I only have two significant figures there. 5.5 moles, because the molar mass of hydrogen only had 2. And for oxygen, 1.81 moles. What we're doing here, and this is a bit of a jump, is we're being asked to calculate the ratios. I do this, here's how. I take my values and I find the individual ratios of each element or chemical species inside the formula. For example, and I always put the larger one on top. It makes things a lot easier. Moles of carbon divided by moles of oxygen, 3.01. Really close to 3. If you see a number that's really close to a whole number, just treat it as the whole number. Hydrogen divided by oxygen, 3.0, 1 decimal place. Carbon divided by hydrogen, 1.0. Well, look at that. Those whole numbers just drop right out in front of you. The ratio, carbon to hydrogen to oxygen, is 3 to 3 to 1. So this means that our empirical formula, CHO, our empirical formula will be C3H3O. The percentage by masses, or, well, I should say the number of atoms within a molecule of this substance, will be in a 3 to 3 to 1 ratio. It doesn't mean the molecule has 3 carbons. It means that these are the ratios of those numbers of atoms to each other. The molecule might be bigger than that. This is the simplest whole number ratio. Here's the next insight, that the molecular formula will be a whole number multiple of the empirical mass. In question 4, you're being asked, calculate the molecular formula. So there might be 2, 3, 4 of these C3H3O units, if you will, in a single molecule. There might be a lot more than there is seen right here. This is the empirical formula, not the molecular formula. You have a formula for that, to find that molecular formula. Here's where it comes from. Here's what you do. You need to calculate a number, large N, capital N. That will equal the molar mass divided by that empirical mass. We figured out the empirical mass, or we can do that, we were given the molar mass. We were told that 1 mole of this substance is 110 grams in weight. It's 110 grams per mole is the molar mass. How about the empirical mass? Here, we need to use the same steps as you use for finding molar mass. 3 times 12 grams per mole. That's your carbon. 3 times 1 grams per mole. That's your hydrogen. 1 times 16 grams per mole. All of these add up to 55 grams per mole. This is not the molar mass. This is the empirical mass right here that we've got. We can use that molar mass and this empirical mass to figure out what our whole number multiplier has to be, that big N. Big N is molar mass divided by empirical mass. The empirical mass, big N then is 110 divided by 55, which is a nice clean division. 110 divided by 55 is 2. This means that our multiplier is 2. So our molecular formula, we can think of it as 2 times the empirical formula. I should almost put air quotes there, really. But that's what it is. We can get that molecular formula by multiplying the empirical formula by 2. So 2 times your C3H3O will give you C6H6O2. That is the real molecular formula for this substance. We had to multiply that empirical formula by 2 to get there. That's question 4 on your worksheet, second page. Question 9. I apologize for the noise in the background. We're given some different information. From your worksheet, your previous worksheet, you learned how to use calculations, what's called the molar volume. I told you that a gas at standard temperature and pressure, which is 0 degrees Celsius and 100 kilopascals, kind of like a cold day at the seaside, occupies 22.4 liters, about the size of a very large balloon. If you see a very large balloon on a cold day, it's about 22.4 liters in volume. Now, for this, I want you to notice one thing. I shaved off one of the significant figures on this. It says 0.850 liters. I really think it would be more accurate to say we only have 2 sig figs. It will not change the answer to the question. Our empirical mass for this substance, well, it's CH2. The empirical mass will be 12 grams per mole plus 2 times 1 gram per mole. This gives us 14 grams per mole. There is another formula on your previous worksheet. We learned that if you have the density of the gas and the molar volume, you can calculate the molar mass. Here's how we do it. We're told that we have 1.59 grams of this substance. It occupies 0.85 liters. That's about 1.9 grams per liter. I kept in that one of those sig figs, and you should actually keep your sig figs in your calculator until the end so you don't make any rounding errors. So it's about 1.87 grams per liter. In the final answer, I'm only going to keep 2 significant figures. Please pay attention to your sig figs. A lot of you need to do that. The mass of 1 mole, this line right here, is a formula. It is the density times the molar volume, 22.4 liters per mole. The mass of 1 mole then is going to be that density, 1.87 grams per liter, times your 22.4 liters per mole. Look at that. It magically gives us that grams per mole. That is the molar mass, 42. This is the molar mass of the gas in question. Now, we are able to calculate that multiplier, that capital N value. We have the empirical mass, and we have the molar mass. Look at that. Here it comes. N is the molar mass divided by the empirical mass. You might have noticed that sometimes I use M mole and M emp to show molar mass and empirical mass. 42 over 14 is 3. Our multiplier is 3. So the molecular formula will be 3 times that empirical formula. I put air quotes here. 3 times CH2, which means we have C3H6. 3 times 1 is 3. 3 times 2 is 6. C3H6, which, by the way, is the same as the molecular formula for propane gas. Question 14 is the last one I'm going to review. The rest of them are very similar, or they're similar to questions from the textbook. Here, we have a substance that is an oxide of mercury. Mercury is that metallic metal that you might be familiar with that's used to be used a lot in thermometers. They use X and Y right here, which is maybe it makes this question a bit more challenging. This is just a way of saying that It's an oxide of mercury with X number of mercury atoms in the formula and Y number of oxygen atoms. We need to figure out what X and Y are. We are told this. We are told we have a mass of this substance of 2.5000 grams. Someone had a very accurate scale. We're told that we have 2.405 grams of mercury that is released when we decompose this substance. We break it down. From this, we can figure out that we had, apologize for the noise. We can figure out that we have 0.095 grams of oxygen. I want you to notice the subscripts again. You should get used to using subscripts. The M little subscript Hg tells us mass of mercury. M little subscript O tells us a mass of oxygen. We can calculate moles. Mass divided by the molar mass is moles. But where do I get those molar mass values? Well, I get them from the periodic table. Here. Moles of Hg, chemical amount is shown with the letter N. So N of Hg, moles of Hg, will be that 2.405 divided by this molar mass. 200.6 grams per mole. That's from the periodic table. Gives us 0.01200 moles of mercury. I find we have 0.0059 moles of oxygen. Now we divide. We take the big number, moles of mercury, and we put it on the top when we divide with the smaller number on the bottom. Moles of mercury divided by moles of oxygen. Well, 0.012 divided by 0.0059 is approximately 2. Taken to two significant digits, it is. It's 2.0 with two significant figures. So the ratio of mercury, Hg, to oxygen, O, is 2 to 1. This means that our empirical formula is Hg2O. We haven't calculated the molecular formula here. It might be Hg2O, but we haven't figured it out. We would need more information to find that. That's everything for my outline for this worksheet. The other problems in the worksheet are similar to these problems that you've seen right here. The next thing I'm going to do is film a lab for you guys, and then you'll have work for a good space of time. Certainly nothing else to worry about for a bit. I hope that helps. And again, I say, remind you, do the readings, watch the other videos.